My name is Anna Lebet. I'm the chair of the J. Robert Oppenheimer Memorial Committee. And on behalf of the committee, I would like to welcome you all this evening. This is our 53rd J. Robert Oppenheimer Memorial Lecture. The J. Robert Oppenheimer Memorial Committee is a non-profit organization dedicated to honoring the intellectual and ethical legacy of J. Robert Oppenheimer, scientific director of the Manhattan Project. The committee is composed of 25 members of the community who work to preserve the organization's 5-decade tradition while developing new initiatives that advance our mission. Our core activities include sponsoring this annual memorial lecture here in Los Alamos, featuring internationally renowned scholars such as tonight's speaker. We also promote science education at all levels, from elementary school, middle school, through high school. We support also school-based programs, including developing educational field trips, such as the recent Pojoaque Valley Middle School visit to Valle Caldera, or the hydrology activity in their classroom, as well as we support science fairs, history fairs, and other school and state-level academic competitions. We also partner with organizations such as the New Mexico Consortium, the Pajarito Environmental Education Center, Los Alamos Historical Society, and neighboring Native American communities, including Santa Clara and Jemez Pueblos, to support the preservation of language and culture. We do all that while fostering intellectual curiosity through public lectures, educational programs, and community events. A critical component of JROMC mission is inspiring the next generation through educational opportunity. We do this by providing scholarships to talented students from Los Alamos, Pojoaque, Española, Santa Fe, and Jemez Valley. Throughout its history, JROMC has awarded approximately 352 scholarships and other awards totaling more than $942,000. All this, of course, is possible with your generosity and the support from local families who have established scholarship endowments in honor of loved ones and in support of future generations. This year, 24 exceptional students were selected as JROMC scholarship recipients. I would like to ask those scholarship recipients in the audience to please stand up so that we may recognize your accomplishments and offer a round of applause reflecting both our admiration for your achievements and our confidence in your future contributions to society. We had a banquet last night with the scholarship recipients, and I can tell you it's pretty impressive, their accomplishments and their aspirations. So we want to congratulate all of you, and we are proud of your accomplishments and look forward to many ways you will contribute to your communities, our nation, and the world. The Oppenheimer Memorial Lecture Series began in 1972 and has brought some of the world's most distinguished scholars to Los Alamos, here in our town. Nearly 20 of them were later nominating for the Nobel Prize. Each memorial lecturer has earned international recognition for advancing humanity's understandings of the universe, our planet, our societies, and the scientific and engineering endeavors that shape the challenges and opportunities facing humankind. We are delighted that Los Alamos National Laboratory's Deputy Director for Science, Technology, and Engineering, Pat Fitch, has joined us this evening. Pat has long been a champion of scientific excellence and education. Please join me welcoming Pat Fitch as he will introduce tonight's speaker. Thank you.
thank everyone for coming out tonight. I also want to thank the J. Robert Oppenheimer Memorial Committee and all the donors and volunteers that made tonight's lecture possible. Think about it, going to an asteroid, for whatever reason, is the stuff of Hollywood. In fact, I did a little research. In 1969, there was a movie called Moon 02. As recently as 2025, a movie called Asteroid. And since we're in Los Alamos, I absolutely am required to mention 1998's Armageddon. Tonight's speaker is going to discuss something far more spectacular than what Hollywood had to offer. Going to an asteroid to help explain the building blocks of life and the origins of our solar system. He's the Regents Professor of Planetary Sciences at the University of Arizona and Principal Investigator of NASA's OSIRIS-REx asteroid sample return mission. Of his many awards and recognitions, I wanted to pick a few to highlight tonight. There's a bunch more in his bio and online even more. The OSIRIS-REx team received the Collier Trophy, awarded by the National Aeronautic Association for the greatest achievement in American aeronautics or astronautics. The same year, 2024, the mission was recognized with the Michael Collins Trophy for current achievement from the Smithsonian's National Air and Space Museum, my favorite museum, the Smithsonian. And Neil Armstrong Spaceflight Achievement Award for the American Astronautical Society, my favorite Purdue graduate. And the Goddard Memorial Trophy from the National Space Club. So without further ado, please join me in welcoming Dr. Dante Lauretta.
Thank you, Pat, for that introduction. Can we get the slides up, please? Thank you so much. I also want to thank the J. Robert Oppenheimer Memorial Committee for this amazing honor. It's been a wonderful visit to Los Alamos. The hospitality has been fantastic. I got to see some of the amazing planetary exploration activities at Los Alamos National Lab this morning, so thank you for that great tour. And I'm especially impressed with your body of scholarship winners. Gives me hope for the future to see such bright, young, eager minds willing to take on hard problems to help society and to really make a contribution to this great nation. So amazing work all around, and I'm very proud to be your lecturer this evening. And tonight I'm going to take you on a journey that goes back in time and a journey that addresses some of the biggest questions that we face as a species. Where did we come from, and are we alone in the universe? So as we look out into the night sky, this is an amazing image from the James Webb Space Telescope of the Carina Nebula. And what's happening here is, this is called a giant molecular cloud, you can see filling the bottom of the field of view. And this is a stellar nursery. This is where stars are being born. And as we've learned with our surveys of nearby stars in our galaxy, planets are very common. At least half of all the stars that we survey have planets in orbit around them, and they form together. Stars and planets form through a common process. And that process looks a lot like this. Here we're looking at what we would call a protoplanetary disk that spans about the size of our solar system, maybe 100 astronomical units. It's in the very early stages of the collapse of that giant molecular cloud, and because of the conservation of a property in physics called angular momentum, not all of the material falls into the center and forms the star, but a fraction of it spins out into a disk rotating around that star. And most of that gas is hydrogen and helium, the most abundant elements in the universe, but there's a large fraction of common elements like iron and magnesium and silicon and oxygen, and what we're really interested in the OSIRIS-REx mission, the carbon. So when we perform modeling and we look at our meteorite collections of what's happening in these protoplanetary disks, there's a gradient in temperature. Very close to the star, it's hot, and only the elements that can be solid material at the highest temperatures survive as rocky or metallic material. But as you move farther out into that disk, ices start to condense. Not just water ice, but methane, which contains carbon, or maybe carbon dioxide, ammonia, which contains nitrogen. And then late in the history of the formation of our planet, material migrated from the outer regions of that disk, and we think impacted the Earth, transforming it. Because the earliest history of our planet was a very violent epoch. It was very hot. There was a lot of heat from the accretion of the planet. There was radioactive isotopes, which were much more abundant in the early Earth than they are today. And the Earth went through a catastrophic impact that formed the moon. And as a result of that, the surface was covered by an ocean of magma. And this is completely inhospitable to any life as we can imagine it. So somehow, in our history, very early on of our planet, we transformed from this glowing ball of magma into this beautiful oasis that we are privileged to be able to share with the multitude of life forms on Earth today. So we want to understand with the OSIRIS-REx mission the details of this process. In particular, where did the water come that makes the oceans of our planet? Wouldn't have survived on that magma world. What about the air that we breathe today, the nitrogen and the oxygen and the carbon that's all around us? And most critically, today I still think the greatest challenge, one of the greatest challenges in modern science, how did the building blocks of life get to the surface of the Earth? And then how did they transform from rocky material into something we would consider alive? This is the driving goal of the OSIRIS-REx mission and of my career. To answer those questions, going back now 21 years in 2005, we selected this asteroid out of the million plus that we know about in our solar system as the target of the NASA OSIRIS-REx mission. OSIRIS-REx is in NASA's New Frontiers program. The total budget from 2008, really, when we started some concept work, through the end of the mission this year in 2026, is a little over $1 billion US. So we had to think very carefully about where would you go to answer this profound scientific question. And a lot of our early decision-making was engineering-based. We needed an object where we could launch off the Earth. Over here on the left, I'm showing you the orbital diagram of our solar system. So the Earth is in teal. Here's Venus, or Mercury and Venus and Mars. And we decided we needed to go to a population of bodies called near-Earth asteroids. Most asteroids orbit out here beyond Mars, between Mars and Jupiter, in what we call the main asteroid belt. But that's a very expensive proposition. And expensive in spaceflight typically means not only dollars, but energy in terms of fuel and also time. Bennu, our target asteroid, has the orbit outlined in orange here, and it makes it an Apollo-type near-Earth asteroid, meaning it actually crosses the orbit of our Earth. And if you look at the oblique view here, you can see right around the vernal equinox, the orbit of the asteroid crosses that of our planet. It's highly eccentric. You can see it gets closer to the sun than the Earth at what we call the perihelion, and it gets almost out to the orbit of Mars. So it has a longer orbital period of about 1.2 years. So every 6 years, the two objects line up. So the engineering constraint was we needed to launch off the planet, rendezvous with the object, spend a substantial amount of time there, because we knew it was going to be a very tricky operation, get down to the surface, collect material, bring it back to the Earth, and deliver it safely down to the surface of our planet, ultimately to our laboratory so we could make these critical measurements. So Bennu rose to the top because its orbit is perfect for this kind of mission. It's one of the lowest energy objects that is available in the solar system. And then when science got to vote, it's a very dark object. It only reflects about 4% of the sunlight that hits its surface. And we intuited that meant that was probably rich in carbon. Carbon is a very common darkening agent. So we were kind of betting the whole mission on that principle that dark meant carbon rich. And it wasn't a completely wild guess because we do get fragments of asteroids that land on the Earth, and the dark ones are typically the most carbon rich. It's about 500 meters in diameter, so a little over 1,600 feet. It's about the size of the Empire State Building as tall. And it's a really fascinating object because you can see it's almost a sphere. It's got quite a rounded surface, which is unusual for such a small body. Usually planets become spheres because they have liquid interiors and they can reach equilibrium with the gravitational force, and that transcribes a spherical shape. And that's not too different than what actually Bennu is like. So hold that thought as we go on our journey to this asteroid. The mission was a partnership between the University of Arizona, which is my home institute, Lockheed Martin, which is based in Littleton, Colorado, and they built the spacecraft. Over here on the left, I'm in their test facility as we're going into vibration testing, getting ready to ship to the launch site, and a NASA center, and we work with the NASA Goddard Space Flight Center in Greenbelt, Maryland. Couple items on the spacecraft that you can see here over my left shoulder is the sample return capsule. So this is the hardware that's going to deliver us back through the atmosphere, and it's going to kind of become the star of our show towards the end of our story. There's a bunch of science instruments on here, cameras, visible, near-infrared spectrometer, thermal spectrometer to look at the heat coming off the asteroid, a laser altimeter to make topographic maps, and in fact, the model that I was showing you is actual LiDAR data with our imaging overlain on the top of it. And then you can't really see it here, but you'll see it on the next slide. This is a 3-meter-long robotic arm, which is the only device that's designed to touch the surface of the asteroid and collect the material in a brief 5-second touch and go on the asteroid's surface. Over here on the right, we're in Florida, the Kennedy Space Center, in 2016 as we're preparing to launch on our journey to the asteroid Bennu and back. And this is the high gain antenna. It's about 2 meters in diameter. This is how we send all of our data back to the Earth and also how we receive commands on the spacecraft. And you can see it's solar powered. These are 2 meter by 2 meter solar arrays, one on each side. We also kind of use these as solar sails. We could use the solar radiation pressure to push us around in the microgravity environment of the asteroid. And what I love about this facility was the history. You can just see all along the wall here all the famous NASA missions that had preceded us into deep space, like the Hubble Space Telescope and the Phoenix Mars lander and the New Horizons Pluto probe and countless others. And you could just feel that sense of history, very much like being the Oppenheimer Memorial Lecture of those who have come before you and laid the groundwork for the path that you're about to take. This is the TAG SAM, so we love our acronyms in NASA world. This is the touch and go, so we're going to touch, grab, and get out of there. We weren't going to stay on the surface. Sample acquisition mechanism. So here is the complete robotic arm deployed, and this is the sampling head here. It's about 30 centimeters in diameter, and it looks for all the world like an air filter you would put on the carburetor of a 57 Chevy. And it's about the same technology. It's basically an air filter made out of aluminum with some stainless steel. And there's no air on the asteroid. It's an airless body. It's too small to hold on to an atmosphere. So we brought our own air. That's what these bottles are here. So we had 3 of them, meaning we could try 3 times to collect the sample. In reality, psychologically, I don't know if we could have done that, but that's a different part of the story. And the strategy is you push the filter down onto the surface of the asteroid, open up a gas bottle, and it creates a high-pressure bubble underneath it, and then that bubble expands and pushes rock and gravel and dust into the filter. The gas escapes through the mesh, and the rocks get trapped in the chamber inside. And then once that is successful, we open up the sample return capsule like a clamshell. There's a capture ring that's custom designed to grab onto this filter head. And then we can use the robotic arm to place the entire head, and then we had separation bolts and tube cutters to remove the head from the arm and close up the capsule and get ready for the journey back to Earth. That was a pretty good day. September 8th of 2016, we're coming up on our 10-year anniversary of launch. It's hard to believe it's gone by so fast. It's been such an exciting, amazing adventure. One of the things I love to do is combine science and art and humanities. And so we had a full-time graphic artist on staff. She helped with, she actually started as a student from the University of Arizona, and then we hired her on when she graduated. She helped with preparing figures for scientific journal articles, infographics, social media posts, and things like that. But I think my favorite product of hers was an annual commemorative poster for the 6 years that we were in flight, 7 years that we were in flight for the Prime mission. So here we are in September of 2016, that launch video that you just saw. And if you remember from the orbit diagram, the orbit of Bennu is inclined about 6 degrees. So it's not exactly the same plane as the Earth. And when you launch, you're in what's called the ecliptic plane. So we had to make a plane change, which is one of the most energetic maneuvers you can do in deep space. And we didn't have enough fuel for the spacecraft to just fire its engines and make that plane change. So we spent a year going around the sun, lining up a rendezvous with the Earth, flying underneath the South Pole, over Antarctica, across Australia, and using the Earth's gravity field as a slingshot. And we call this maneuver the Earth Gravity Assist, and it's very common now in planetary exploration because you can get a lot of velocity change on your spacecraft basically by stealing a little bit of momentum from our planet. And that gave us the trajectory to allow us to arrive at the asteroid in December of 2018. We spent the entirety of 2019 mapping this body in exquisite detail, and still the highest resolution global map of any object in the solar system. Imagery and LiDAR data at about the centimeter scale across the entire object, because we had very specific requirements. We had to put that filter down on a spot on the asteroid and pick up rocks that were about 2 centimeters, or a little under 1 inch in diameter, is what we could ingest. So we were looking for smooth patches of gravel or sand. In fact, I even said sand many times because our astronomical data interpretation was such that the surface of the asteroid was going to be relatively smooth because of its radar properties, a property called radar roughness, its thermal emission properties, how fast it heats up and cools off. It turned out not to be the case, as you'll see. So it was an agonizing year. And then in December of 2019, at the American Geophysical Union meeting in San Francisco, we announced the winner of our site selection. And then COVID hit. So 2020 was the year of TAG. And we had originally planned to do it in August, but because of COVID and the remote work adjustments, we delayed that until October of 2020. We couldn't leave the asteroid until May of 2021 because we needed those orbits to line up. So it's kind of like you have to wait for a launch window to leave the Earth to get to the asteroid. Well, you have also a departure window to leave the asteroid on a trajectory that gets you back to the Earth, targeting sample return in September of 2023, and then setting up the final phase of the mission, the sample analysis campaign. And we had originally been scheduled to end the mission in 2025. We did have some challenges on the ground. We had also saved a fair bit of money in our budget, and so NASA agreed to extend us to September of 2026. So we only have a few months left in this amazing journey, which for me has now spanned 22 years, and officially as a NASA program, 15. So these are some of the first images that we saw when we made our approach to the asteroid. And several things struck me here that would drive our operations concept as we move forward. First of all, there's no sand. It's all giant boulders, rough, rugged, rocky objects on the scale of this building and larger dominate the surface. It also, if you notice, it's a very dark asteroid, right? 4 to 4.5% reflectance, but there's these really bright spots that show up throughout there, and I characterized it saying it looks like salt and pepper, mostly pepper, but little bright white flecks that kind of gave us that impression. So I knew right away there was going to be several challenges here. First of all, there was no obvious location that met the requirements for the TAG SAM to be put on the surface and collect a sample. Everything was way smaller than our guidance system was going to be capable of targeting. And then we were going to use the laser as our guidance system on the way in. It was going to be measuring the distance to the surface and telling us how fast we were approaching and be our safety tool. But these little specks of salt were going to make that very difficult because we designed the laser to reflect off a 4% surface, and these things are 30% or higher in their reflectance. So it was going to saturate the detector, and then that would cause all kinds of problems. So we had 2 reasons to redesign our guidance system in flight with a software patch as we were trying to pick a location where we could collect the sample. So we went from the LiDAR-based approach, which had a very large uncertainty, about 50-meter uncertainty, to an optical approach called natural feature tracking, which, as you'll see, got us very close to our target location. So it was almost the day of the first data when I called up the team at Lockheed Martin and I said, I think we have a problem. I don't think our guidance system is going to work. And we had thought about the natural feature tracking and set up the system to be able to upload software if we needed it. And so I told the team, get busy, we're going to need NFT. The geology on this body is stunning, and if you are any kind of geology fan, I invite you to go online. All of our data is available publicly. There's thousands and thousands of images. There's still a lot of science to do with the remote sensing data that we collected at the asteroid surface. And what we saw was that there was kind of 2 broad categories of boulders. Note the 10-meter scale bar, right? So that's 30 feet. That's like a 3-story building size right there. The really, really dark stuff, like this one here we call the gargoyle or chinquilla, all the features on Bennu are named after mythological birds because Bennu is a mythological bird, the Egyptian heron associated with the Egyptian deity Osiris. These are really dark. These are like 3% reflectance, and they have this kind of rough texture to them. We called them hummocky boulders. They're the biggest objects on the asteroid, usually 30 meters or larger, up to 100 meters in diameter. And you can kind of get a sense of the challenge that we were facing. This is one of my favorite images over here on the left, right? So this is 10 meters, so gargoyle's about 15 meters tall. And we need to pick up something that's a couple centimeters in diameter, right? And you look around here and you can see this is nothing. Look at these giant rocks that are just hanging off the limb here. With one exception, this little patch in the image right here kind of looks like the stuff that we were going after. In fact, it has a giant rock sitting right next to it, which is not what we were hoping for, but this one gave me some hope that maybe there was some fine-grained material available on the surface. The second category of boulders have very different shapes and structures to them. We call them angular. They tend to have very sharp, planar faces, very well-defined angles associated with them, and they tend to be brighter, to the 6 or 7% reflectance. And they're smaller. You can see the scale bar here, 2 meters, 4 meters. This one is, I think, the biggest one on the surface at just about under 10 meters in size. And we'll come back to the hummocky and the angular in a bit here. And then there were these really rare occurrences, like you see right here, this bright white material, linear feature embedded inside a boulder. And it looks like these are the really, really bright stuff. This is 30% reflectance or higher. In fact, it's so bright. Again, we built cameras to image 4% reflectance surface. And so something at 30% or higher just saturated. Every image of these features is saturated in the detector. So we don't have a quantitative number, we just have a limit on how bright they need to be to do that. And these, we used our spectrometers to identify the mineralogy, and they look like a common mineral type called carbonates. I don't know what the water's like here in Los Alamos, but in Tucson, where I live, it's very hard. There's a lot of calcium and carbon dioxide. And when the water evaporates, it leaves those white residue, clogs your shower heads. That's carbonate, calcium carbonate, or calcite. That's what this looks like. And we see these kinds of features on Earth, and this was a very exciting discovery for us because this is the indication of a hydrothermal system. Water that's been heated up and flowed through, it scavenges the calcium, it scavenges the carbon dioxide, and as that system cools down, it deposits these veins as precipitates or as the water evaporates as evaporite minerals. So we were very excited because hydrothermal alteration is a key concept for the formation of organic molecules leading to the origin of life. We see these systems on the floor of the ocean here on Earth. They're called the hydrothermal vents, or in the case of the carbonate-rich ones, the alkaline hydrothermal vents, or colloquially, the white smokers. And these are big. These are almost a meter long and maybe up to 10 centimeters thick. And so this shows us that we had hydrothermal deposition and flow on Bennu's parent body. And this is an important concept. Bennu is only 500 meters. That's pretty small as asteroids go, especially when you get out to the main belt. The largest one is Ceres at over 1,000 kilometers. In order to have this kind of sustained flow, you couldn't do that on a small body like a 500-meter asteroid like Bennu. This suggests that Bennu was once part of a much larger object that was then shattered. And that kind of explains the textures that we see here. This is kind of just a random accumulation of material. There's no basalt flows like volcanic flows. There's no ponding or anything like that. It looks like a random mix of boulders and gravel. And that's because it was part of a much larger body that was shattered catastrophically in the main asteroid belt. And these are some of those fragments that just collapsed back gravitationally to form what we call now a rubble pile asteroid. After all of that work, in December of 2019, we selected this site in the northern hemisphere called Nightingale. It's in a crater called Hokioi, and for scale, this is about 20 meters across. And remember, the original guidance accuracy was 50 meters, which would be bigger than the entire field of view. And I do want to brag, this is real topographic data from the laser altimeter overlaying with our imaging at the highest resolution. And you can see why we like this spot. It's full of fine-grained material. It looks like a very fresh impact crater. Small asteroid hit the surface of Bennu, excavated this material, and exposed what we now know to be a layer of fine-grained material underneath the surface of the asteroid. And we explain this using a metaphor called the Brazil nut effect. So if you've ever gotten a can of mixed nuts and you shake it up and you open it up, the big Brazil nuts are always sitting on top and all the little peanuts have sank down to the bottom. That's a natural size sorting mechanism whenever you have shaking of a granular material like the surface of Bennu. So this became our target, and we spent the next 10 months getting the team ready to send this amazing spacecraft that we all had come to know and love and really personify. We feel like it's part of us, down to the surface of this asteroid to collect this sample for scientific treasure. I love to show this video because this is what we made before we arrived at the asteroid, pre-launch video. And it shows you kind of what we expected to happen. Here comes Tag Sam. You can't see it maybe so well here, but this is a nice sandy, smooth surface with no boulders or anything in our way. We touch the surface for 5 seconds. We shoot our little gas bottle and we collect the dirt and we fly away. If we're happy with what we collected, we open up the capsule. We tuck the sample head inside there. You can see the capture ring right there. Cut the bolts and the tubes, stow the arm, close up the capsule, and bring our journey home, or bring our sample home. Now let's look at what really happened. So this is real images from the contact with the asteroid surface. A couple things to note. We were coming in at 10 centimeters per second. That's about the speed of a baby crawling. We're just sneaking up on this thing. We don't want a lot of dynamics with the spacecraft. The second thing is that a lot of stuff explodes right after we fire the gas bottle, including some giant rocks like that one right there. And what I noticed right away is that the head is in shadow, which means we're sinking. We're digging a hole. What we found out was that it took, we had a 1 second delay. We had what's called the inertial measurement unit sensing contact. 1 second went by to settle onto the surface, and then the gas fired. About 6 seconds later, the gas was done. Our 5 seconds was up. We were still moving down into the asteroid at 4 centimeters per second. We thought we were going to hit a solid surface, and we hit a pool of quicksand. There was absolutely no resistance to the downward motion of the spacecraft from the contact. The 6 centimeters per second deceleration was from us because we fired the gas. So we shot the gas out to the bottom of Tag Sam, and that slowed us down. So as planned, the spacecraft fired its thrusters. There was 8 of them, 2 on each corner on the front deck, and that initiated the back-away maneuver. So I knew right away when these data came down that something interesting had happened and that was unexpected. The other thing you notice here is we get to this, what I call the blizzard phase, where you see lots of fine dust flying around. And I was like, that's the beach that I was telling you about. It was just buried by the Brazil nut effect. So we just had to dig down a little bit, about 10 centimeters, to get to that layer. That was all great news. This is a second camera called the nav cam. It's looking off to the side. So here's the shadow of the robotic arm coming in. We make contact right here. You can see now a much wider field of view and how agitated the surface is. When we first saw this images, we weren't even sure what we were looking at. But eventually, as you start to look, especially in this upper right corner, you can see some of the large, these are meter-sized boulders that we've kicked up, and you can see they're plate-like and they're tumbling away from us. And then now you can see this is the rim of a crater that we're excavating with the tag SAM. And then this is what I call the scallop. This is where the thruster is hitting, and it's pushing away all the small dust and just leaving the big rocks behind. And you'll see the surface of the asteroid come into view here, and you'll see shadows as the rocks fly across the surface. We saw collisions. So what it took was an additional 3 seconds of thruster firing to stop moving deeper into the asteroid. So we were sinking for 9 seconds total. We penetrated almost 50 centimeters, about the length of my arm, deep into the subsurface of the asteroid. Scientifically, this is actually fantastic because we were a little worried the stuff right at the surface had been exposed to the solar wind and to radiation and was going to be different than the bulk of the asteroid. So the fact that we went so deep is great news for science. It took almost 26 seconds of firing our engines to back away. And it was 17 seconds that we were in contact with the asteroid surface versus the 6 that we had planned for. And then we saw this massive debris plume excavating tons of material. So this was a fantastic result, not just because of the collection was going to be really efficient, but we learned a lot about the nature of these rubble pile asteroid surfaces. They're highly unconsolidated. There's no cohesion making the grains stick together. We thought if it's organic rich, maybe they're kind of gooey or gluey or tarry, and they would be sticking together and giving the surface some strength. None of that. It was, if we hadn't fired the backaway thrusters, the spacecraft would have just dropped into the crater and disappeared, buried in the asteroid regolith. So we had to redo the movie, right? Right? So it was like, okay, we went back to Goddard's Scientific Visualization Studio, and now you can see there's no flat surface here. We got giant protruding rocks everywhere. This is all, again, real data. We hit the surface, and we sink, and we sink. We excavate a large amount of material. Some of that gets redirected as the thrusters fire to stop the downward motion. And every time I watch this video, I think back to, this is a competitively selected mission, and the last stage is the site visit, where there's a panel of experts from all across NASA and industry and academia, questioning everything you're going to do. And if I had showed this video at the selection board and said, this is the plan, we're gonna bury a $1 billion spacecraft 50 centimeters deep and throw up a bunch of rocks at its face, and it's gonna be fine. And it was, actually. The spacecraft is a tough vehicle. Lockheed did a great job for us. The solar arrays, this is the active area of the solar arrays to prevent dust from accumulating there. We were worried the heat shield of the sample return capsule might have taken some damage. It looked good. The radiators, which dump out the heat to deep space, were working. The only real impact that we saw was all of the optical surfaces got coated with dust. One of the nav cams lost about 60% of its transmission. That was the most dust that we saw, but all the instruments had dust coatings. But it was like, well, we don't care because we're done. We got our sample. And that's what the mission was there to do, and now we need to get home. Except we didn't expect all of that. I was sitting there in my hotel room in Lockheed, in Denver, and I said, we did not expect this. We didn't plan to go back and image the site, because we thought we were going to dig a hole like we did in the laboratory, including microgravity testing, that was going to be 30 centimeters across, and we would never find it on the surface of the asteroid. Targeting something like that is really, really challenging. So I went to the team and I was like, change of plan, we're going back. And we're going to image the surface and we're going to see what we did, because there's a lot of important science information about the nature of these asteroids. So here's the reconstruction. Here's that 3D shape model. Here's the crater. This is where we contacted. And then we're able to reconstruct a topographic map just from our imaging data. This is the crater that we excavated. It's about 8 meters in diameter. We predicted 30 centimeters. We excavated 8 meters across. About a meter depth. You can see where the thrusters hit. You can see that this ridge of material, what was really fascinating is because the asteroid's rotating every 4.3 hours, we lofted the plume, the asteroid rotated, and then the plume dropped down to the west. And that's what this ridge here is our ejected material falling back down onto the asteroid's surface. So we were able to predict the cohesion, the bulk density of this material, and it's about 1/6 the density of your average rock, like the beautiful basalts and tuffs you have around here. And it's less than half the density of the bulk asteroid. So it was a really special kind of ponded area on the surface and turned out to be great for sample collection. So we successfully got the tag SAM into the sample return capsule. We tucked it away and said, night, night, we'll see you in 2.5 years. And this is what we had expected. So we thought we saw a lot of dust, really fine dust, kick up so that we'd have submicron particles. And the largest particle we could see was about 3 centimeters, which was right at the ingestion limit of the device, actually a little bit above, but somehow it snuck in there. And based on all of our spectroscopy, we expected the sample to be dominated by hydrated minerals, minerals that have locked up water into their crystal structure because we're dealing with hydrothermal environments, not volcanic environments. And we call those kinds of minerals technically phyllosilicates, more colloquially clay minerals. Those carbonates, like in those veins, we saw iron oxides, especially the one called magnetite, otherwise known as a lodestone, also a very common hydrothermal product. We inferred sulfides. Can't see them with our spectrometers, but sulfur is a very common element and it's in all of our meteorites. And tantalizing clues that the surface was organic rich. Again, from the visible infrared spectrometer, we saw absorption features towards the longer wavelengths that are very characteristic of bonds between carbon and hydrogen, also between carbon and oxygen. So this is what we predicted, and we spent the next several years getting ready on the ground to receive this sample to go to that final phase of laboratory analysis. So this is now September of 2023, September 24th, and this is an animation, clearly. So we released the capsule about 60,000 kilometers away. We spin it up just a little bit to stabilize its flight through the atmosphere. It has no guidance capability. It's like the quarterback throwing the perfect spiral pass on the Hail Mary and hitting the end zone. In this case, the end zone is the Utah Test and Training Range, southwest of Salt Lake City, which is the largest Department of Defense controlled airspace in the United States, continental United States anyways. So it's a great place for bringing in stuff from outer space. Here's the actual images, that same nav cam. So you can see the capsule being released here. The sun is off the field of view, and that's the limb of the Earth right there. So it's phenomenal, the precision with which we can control these vehicles over these enormous distances. OSIRIS-REx traveled over 7 billion kilometers in its journey from Earth to Bennu and back again. And we were able to fire those engines once in May of 2021 and end up here with a little bit of targeting right at the end, and then release this capsule and hit a 50-kilometer patch of Utah desert on the surface of our planet. So the final moments. Before that, so the capsule was launched towards the Earth. The spacecraft, with all those great science instruments and the communication systems and power and all of that stuff, is in great condition. So the flight dynamics team, or the navigators who plot our path through the solar system, are brilliant and motivated, and so they figured out a very crazy path. So here we are in 2023. We have to divert, or else we'll follow the capsule into the atmosphere. We don't want to do that, and that was always the plan, to just park it. But we could do a series of perihelia, get very close to the sun, much closer than we were ever designed to, use gravity assists and deep space maneuvers to switch it up so that we arrive at a different asteroid in April of 2029, a very famous asteroid. You might want to put this on your calendars. April 13th of 2029, asteroid Apophis, which is 300 meters in diameter, is going to come within 30,000 kilometers of the Earth, which is right about the orbit of our geosynchronous weather satellites and observation satellites. It's the largest, closest approach of an asteroid for about 5,000 years. The biggest asteroid in recorded history. And if you are in Eastern Europe or Africa, you'll be able to see it with your naked eye. So we think it's going to be a global campaign. People are going to get very interested in Apophis. And we need that last gravity assist. Just as Apophis is doing close approach, we'll do a close approach and we'll arrive a couple weeks later. And we'll go into orbit, and we won't be able to collect a sample, but we'll be able to do everything else that we did at Bennu with the mapping and the spectrometers. And even the tag event, we're going to send the spacecraft down and just fire the thrusters and blow away the surface and do all those granular mechanics experiments that we saw. So it's been rebranded as OSIRIS-APEX for the Apophis Explorer. I am not the principal investigator of that. I hand that over to all the people who were early career members of our team on OSIRIS-REx. They've now been promoted up into leadership roles, science team management roles, et cetera. So it's the next generation is taking the spacecraft on this amazing new adventure. And I am the emeritus PI, so I'm there to help them. And I'm kind of the corporate memory. I remember a lot of things. Back on Earth, everything worked perfectly, well, almost. I won't go into the details, but we had some nail-biting moments. The parachute opened very late, but it did open. And this was the image that we saw as the capsule made its gentle descent into the Utah desert. And unfortunately, it goes right behind this ridge, so we lose it, but you'll see the parachute deflate, so we know we're on the ground, and we can get out there and collect our treasure. There it is. It was a perfect landing. You can see it's now all black and charred because of its fiery passage through the atmosphere. And when I was at the lab today, I heard of some cool experiments that were done to monitor its passage through the atmosphere, so that was exciting to hear about. Here's the parachute sitting right next to it. And you can see we're on the salt flats of northwestern Utah here. So I was on the welcoming committee. I mean, it's not every day a flying saucer from outer space lands in the Utah desert, right? I don't think. So I was there to greet it, but more importantly, I was on the environmental contamination committee. So I was making sure that the sample did not get exposed to the Earth's atmosphere, that it didn't pop open and samples spill out, or some of the Utah dust get in there. So we collected air and soil and dust and vegetation and pretty much anything that was in this area around the capsule we have archived as part of the collection, all of which is now at NASA's Johnson Space Center in Houston, Texas, right next door to the Apollo Lunar Collection and available for the worldwide scientific community. So we quickly packaged it up. We shipped it to Houston, where our curation facility was waiting for us. Got it into the custom-built glove boxes. So one of the most important aspects of the mission was to keep it organically pristine, because we want to understand if the building blocks of life are in the sample. The last thing you want, and the reason you can't do this experiment with meteorites, is as soon as it's exposed to the Earth's atmosphere, bacteria, they love these rocks, and they actually eat the organic molecules in these carbonaceous meteorites. And we have to do everything in these nitrogen-purged glove boxes to keep that sample pristine. Here's your principal investigator cheering, because the first thing we saw when we opened it up was this beautiful distribution of black asteroid dust. We call this the avionics deck. Here's the capture ring, here's the tag SAM head, there's the gas tube that delivered the nitrogen to blow down and push it up. You can see, because of the late parachute deployment, we actually tumbled for a little while through the atmosphere, so stuff got mixed around. And then we had it on a purge as soon as we got to it to blow any potential contamination out. And that's what pushed all of this to the outer edge. This was actually a metal braided seal right here that created that pattern. This was great news because we had a lot of work to do to disassemble this hardware, but because of the material that was sitting out on the avionics deck, literally within 2 days, we were in the laboratory at Johnson Space Center analyzing the sample. This is the bulk of the collection. So we returned a total mass of 121.6 grams. The mission requirement was 60 grams, so we did better than twice. If you're doing quick math, that's about $8 million a gram. Bargain, I would say. This is the biggest piece right here, so that's 3.5 centimeters. Most of it is really dark. One of the things, and this image has even been stretched a little bit, when I saw it with my own eyes, it looks like holes in the aluminum. This is all aluminum trays here that we use, and these are 1 centimeter tick marks here for scale. But this one, the big one, we actually call the heart, because it's got a nice little heart shape, has that bright white stuff on its surface. So I was like, okay, we might have gotten some of the carbonates. That's what we were really hoping for. Now let's take a quick look at the nature of the collection. So remember, hummocky, angular, and the vein-bearing rocks, kind of the three main geologic categories on the surface of the asteroid. And meter scale bars here. Now look at the sample. Over here, 5 millimeters, so half a centimeter scale, we have hummocky particles. And then we go down here and look at these really beautiful geometric angular particles. And then we have these, what we call the mottled particles, like the heart, which has this crusty material, and smaller pieces throughout the collection. So somehow, the morphology of the boulders at the meter scale is mirrored when you get down to the sub-centimeter or centimeter scale for these stones. And we haven't quite sorted all of that out yet. But this tells me that we've probably captured a good part of the diversity of what was on the surface of the asteroid, because we have the different textures and the different mineralogies, and we're seeing a lot of variation in the sample. Still a lot of work to do. So that was all great. The space flight end was over, the space flight part of the mission, but the reason I got into it is because I'm a geochemist, and I want to understand these what we call astrobiology questions about the origin of Earth's organics and volatiles and the origin of life. This kind of captures all of the different scientific thrusts that we have in our sample analysis program, but this is the one that really drove me, and it still does to this day. And I went back to the final report we submitted to NASA in 2010, the concept study report, and I read what I wrote and what I promised, not just NASA, but anybody who's an American taxpayer. This was the promise we made to you and to the scientific community worldwide. And it said, analyses of these samples provide unprecedented knowledge about pre-solar history through the initial stages of planet formation to the origin of life. And I was like, okay, that was great in a sales brochure, but how am I really going to do that? Because I'm a guy who likes to deliver on my promises. So that's what we've been focused on ever since. So let's just take a quick tour through what we're finding in the sample. And lo and behold, 70 to 80% by volume are water-bearing clay minerals, like we predicted from our spectroscopy. So we did really well trying to understand the mineralogy. We're seeing kind of at least two different varieties. The one over here on the left is like a rosette. Note the really tiny scale bar here, 5 microns or 5 micrometers, which is 1/1,000,000th of a meter. And one of my favorite parts about giving this talk is I go from a 500-meter scale bar down to a half a micron scale bar, and even smaller in some images. This is a mineral called saponite. This is a different phase over here. You can see it's kind of fibrous. It's called serpentine because it kind of makes snake-like crystals. Common material you might have heard of like this is asbestos. Asbestos is a clay fiber mineral, and it's similar to serpentine. So all of this is clear evidence of those hydrothermal systems. Bennu came from a world where a lot of water was interacting with the rock and putting that water structurally into a lot of these clay minerals. We have a lot of carbon. About 4.5% by weight of the sample is carbon. It comes in many different varieties. We see these, what we call carbonaceous nodules. So these large concentrations of dark, kind of organic tar material. We've gone in and looked inside of these, and they actually have trapped the precursor to the clay minerals, the anhydrous silicate minerals. A lot of it is glassy and has some metals and sulfides associated with it. We see these materials in interplanetary dust particles, and we think they're from maybe from comets that haven't experienced the liquid water phase. So not only do we have a fantastic organic compound here to go and study, but it's trapped inside of it and shielded from the water, the dust that altered to form those clay minerals. So we can start to piece together the entire alteration sequence. Here's the calcite. So you can, these are electron microscope images, which are grayscale, but we colored the calcite crystals just to draw your attention to them. And several things leap out at me right away here is that they're euhedral, meaning they have well-defined crystal shapes, which indicates, and they're growing into veins and voids. So the crystals were able to precipitate from the water and grow in an unrestricted manner. There was no volume that controlled where they were able. So they were growing probably in a microgravity environment, as that water was cooling down and the calcium carbonates were precipitating out of solution. We have some other minerals that look like they clearly precipitated from the water phase or the liquid phase, including iron oxides. These are magnetite framboids, named because they look like raspberries, and the French word for raspberry is framboise. So we call them framboidal magnetites. And they are also very crystalline in their form and grew from the water or the fluid phase without any volume constriction. And we have the sulfide minerals that we predicted as well. And they also have these beautiful kind of hexagonal platelet forms and form very well-oriented crystals. So all of this material looks like it was in the liquid phase, and then that liquid cooled down and precipitated probably the carbonates, the oxides, the sulfides, and some other interesting phases as well. These are sodium carbonate minerals. So we got the cover of Nature in January of 2025, and these are beautiful bladed crystals that are growing again into the void spaces. This is like something you would buy at a gem and mineral show. It's just a perfect mineral crystal structure. And the fact that it was preserved not just through our sample collection and return, but from the catastrophic disruption of Bennu's parent body and the reaccumulation and its drift from the main asteroid belt into near-Earth space. These delicate structures have survived that 4.5 billion year history to get into our laboratories for us to start to unravel some of these questions. And then we get to these modeled particles. You know, I showed you the little carbonates that we had seen, and I thought for sure that these were going to be carbonates, but I think for me this is the biggest surprise of the mission. They're a different compound called phosphates. And from the astrobiology perspective, i.e. origin of life, this is really exciting because phosphorus is a critical element for life on Earth. And it's often the limiting nutrient. A lot of fertilizers are putting phosphate right into the soils. Of the big six that we think about for origin of life, which is hydrogen, carbon, nitrogen, oxygen, sulfur, and phosphorus, phosphorus is by far the least abundant element. And I did a lot of work on this over 25 years ago. My first studies in astrobiology were on phosphorus chemistry. So to have it be the big surprise from the mission is particularly gratifying. Over here is a visible image. So you can see how bright and almost blue tint that these crystals have. And then these are electron microscope images. So this is the same field of view. And now the phosphate looks kind of wrinkly. My son was in the lab with me when we were taking these pictures, and he said it looks like alligator skin. You can see a zoomed in region here, and that's kind of stuck. So we kind of call it the alligator skin texture that we're looking for. And then here is zooming in on this piece that broke off. This was actually just a happy accident. As we were mounting it on the carbon tape for the electron microscope, this fragment broke off, and then the phosphate broke off. So we got a really good sense of the relationship. When you look at what's underneath it, this is classic Bennu material. You can even see the hexagonal sulfides and the framboidal magnetites. So that looks like what most of the sample is. And then this is a thin crust that's been deposited on top of that material. And this is really fascinating because most phosphate minerals on Earth are calcium phosphates. But because we have those calcium carbonates, they stole all the calcium away, and the phosphorus was able to accumulate in the fluid as the system evaporated away. And it has this texture due to desiccation, probably long after its formation. But it's an amorphous, i.e. not a crystalline phase, and it looks like a residue. It's the last of the fluid evaporated away, and this was everything that was left, all the incompatible stuff in the liquid phase, deposited as these phosphate phases here. So when we look on Earth at the environment that produces a similar suite of minerals to what we're finding in the Bennu asteroid samples, we go back to these alkaline hydrothermal vents at the base of the ocean, right at the mid-ocean ridge. And what's interesting is that the heat that's causing these smokers is not the magma from the mantle of the Earth, it's actually the heat that's released from the serpentinization reaction. So mantle rock, which is anhydrous, a mineral called olivine, mostly reacts with seawater. It makes the serpentine, that clay mineral. That reaction releases heat. It's what we call exothermic. And that heat is what drives these hydrothermal vents. So you see the bright white crusty material, that is the carbonate phases. There's the iron sulfides and the magnetites. All of those minerals are forming at these alkaline hydrothermal vents. So this is the environment from the early solar system, the kind of environment that's recorded in the Bennu asteroid samples. And for an astrobiologist, this is a dream come true because we think about these sites as potentially the locations for the origin of life on Earth, maybe 4 billion years ago. And so even if the hypothesis is that asteroids like Bennu delivered the compounds is not correct, what Bennu shows us is we have this kind of geologic sample in a system that there's definitely not life. So we can look at the organic evolution in these environments and extrapolate that back to the early Earth. So both sides of the argument in the community, is it endogenous, formed on the Earth, or exogenous, delivered from space? The Bennu samples help you understand both of those possibilities, either as an analog sample not contaminated by biology, or as the actual source of the material. And you can see, like, there's biology all over. Look at this little crab right here, right? So you can't study these for astrobiology investigations to the origin of life because there's life all over the place. So they're full of biomolecules. And when we look out into the solar system for where do we think similar environments might exist, we're drawn to what we call these ocean worlds. This is a famous satellite of Saturn called Enceladus. And Cassini spacecraft took this fantastic, I think, iconic image as it flew over the South Pole of this moon, because you can see it's shooting these plumes of water and organics and salts into outer space. And we think that there is an ocean, a thin ocean, underneath the icy crust. It's interacting with the floor, probably got some tidal heating from Saturn, and the serpentinization reaction is taking place, and it's driving these geysers. And this actually creates one of the rings of Saturn, the E ring of Saturn, are particles that are ejected out of the plumes of the moon Enceladus. So I think Bennu's parent body was probably something like this. This is about 500 kilometers in diameter. We're estimating Bennu's parent smaller than that at 100 kilometers. But it's the kind of environment we're very interested in today for looking for either origin of life or maybe even an existing biosphere in these ocean worlds around Jupiter and Saturn and elsewhere throughout our solar system. So I'm going to finish up with just a tease. When I was talking to the organizers about the kind of lecture, I said I could give an hour on detailed organic molecular chemistry, if you think the audience would be into that. And they were like, yeah, maybe not. So we got the story of OSIRIS-REx, but we've done a lot of the astrobiology. So what I'm showing you here, of course, is Bennu. And this is the biggest one here, the 100-meter boulder. I call that the rock. ROC, because the rock is a bird from mythology, the one that carried Sinbad around, but it's also a big rock. And then over here on the right is kind of the basic idea, at least the materialistic view for the origin of life. So you start out with basic molecules, things that we know are common in the universe. We can see them with our telescopes. Water, we definitely had a lot of water. Ammonia, one of the big surprises as well is how nitrogen-rich the samples are. About 0.5% by weight is nitrogen. And you remember those hexagonal sulfide crystals that I showed you? One of our graduate students in Arizona has gone in with a transmission electron microscope and found little pockets of liquid ammonia trapped, what is called a fluid inclusion. So not only do we have the minerals, but we have little samples of the fluid as well. Methane, to bring in your carbon, probably also carbon dioxide, your sulfur coming in as hydrogen sulfide, and your phosphate ion. So this is standard chemistry. This is very easy, very hydrogen-rich because we're in a hydrogen-rich environment in the protoplanetary disk. So all of those, there's evidence for either directly or indirectly in the asteroid sample. And then you get up to making things that are interesting for biology. For example, nucleobases are the letters of our genetic code. DNA uses 4. RNA, which is like the messenger, uses 3 that DNA uses and then swaps one of them out. We have all 5 of those and more in the Bennu sample. So the things that make up our genetic code are present as molecules in the asteroid sample. Amino acids, these are the building blocks of our proteins. If you take protein supplements, you can look at the ingredients, you can see all the different amino acids that are in there. There's 20 that are used in biology. 15 of those are in the asteroid sample, along with 17 other ones that are not used in biology. The 5 that are missing are particularly fragile, and they probably wouldn't survive 4.5 billion years of asteroid history, but their precursors for metabolism are present. So you could make the genetic code, you can make proteins. We now have lipids. We have long-chain fatty acids, which make membranes for cells, are present in the sample. And we even have little structures that look like compartments that are surrounded by these fatty acid membranes. We have sugars, like ribose, which is the part of the backbone of RNA. We have organophosphates, which is the other part. So we have all the little pieces. Basically, every molecule that's used important in biology is present in the asteroid sample. But what we're not seeing is them getting together and becoming alive. And as I said, to me, that's the greatest mystery. None of the amino acids are bonded to each other, what would be called a dipeptide. We haven't found even a single evidence of that peptide bond forming, let alone a long chain of amino acids, which would make a protein. We don't have the nucleic acids. We have the phosphates, organophosphates even. We have the ribose, and we have the nucleobases. Those are the 3 parts of an RNA molecule, but they're not connected to each other. And of course, all of that has to come together inside the membrane. The nucleic acid is the recipe to make proteins, and that's what a cell is, and that's what life is as we know it. Everything people would agree is alive is cellular. There's some edge cases like viruses we argue about if they're alive or not. But we don't have these in the asteroid sample, but we got pretty far up the ladder towards the origin of life. And now the future for me and my research is to try to think about how possibly you could get to this final stage. So the question about whether the building blocks of life are common in the universe, I think is a solved problem now. This Bennu is not a particularly rare type of asteroid. It's just rare in the inner solar system. When you go out towards Jupiter, most asteroids look dark and carbonaceous like Bennu. Solar system is full of the building blocks of life. That means not only were they delivered to the Earth, they were delivered to Mars, they were delivered to Venus, they're in the oceans of Jupiter and Saturn, and they're probably all over these exoplanetary systems that we see orbiting nearby stars. So I consider that question answered. We understand that chemistry can get you pretty far down the path to the origin of life. What we have no clue is how all of that gets coordinated, orchestrated, information gets embedded, and that information takes control of the system, and that system becomes something that's alive. So I'm going to leave you with that. I thank you again for this opportunity, for your attention. And I understand we're not taking questions in the lecture hall, but there's a reception afterwards, and I will be there, and I'll be happy to talk to anybody who has burning questions, especially our scholarship awardees and students in the audience. But anybody's welcome. Thank you so much.
Thank you, Professor Lauretta, for such an exceptional and inspiring lecture. At the request of Harold Agnew, the director of Los Alamos National Laboratory, a bust of J. Robert Oppenheimer, the profile here, was created in 1973 by the late Santa Fe sculptor Una Hanbury. The laboratory purchased the first of the 3 casts and placed it in the J. Robert Oppenheimer Study Center, where the lab is 1, this is in TA3. And the Smithsonian Institution also got a second cast, and JRMC obtained the artist copy, the 3rd and final cast, which is currently on display at Los Alamos History Museum. At the JRMC's request, Ms. Hansbury later designed a commemorative medallion using the profile of the Oppenheimer bust that probably you're all very familiar with, and since then that medallion has been presented to each J. Robert Oppenheimer Memorial Lecturer as a token of our appreciation. Professor Lauretta, is now our honor to present you with the J. Robert Oppenheimer Memorial Medallion in recognition of your outstanding contributions to science, and for sharing your insights with us this evening.
Thank you.
Thank you all for attending the 53rd J. Robert Oppenheimer Memorial Lecture. As Dr. Lauretta mentioned, rather than holding a formal question and answer session, we invite you all to join us at the reception. If you go outside to the left-hand side, Professor Lauretta has graciously agreed to spend time with us, with the attendees, especially the students and scholarship winners, and will be available to answer questions and continue the conversation. Also, if you want to know more about J. Robert Oppenheimer mission, if you want to meet some of the board members, please look for those of us with this distinctive name tag. We love to talk about what we do. We want to get your insights. If you want information about how to endow future scholarships or how to donate, we would be delighted. I hope you will join us, and we thank you all for your committed support to the J. Robert Oppenheimer Memorial Committee mission. Thank you very much. Good night.